So we've got two questions here, questions 1 and 2. They're kind of similar, but they're not exactly the same. One is asking about the time it takes for a certain amount of a radioactive particle to remain, and the other one says to decay. So those are the key words here in each of these cases. So let's look at the first one. In the first one, we need to calculate the K value, and we have an equation here that we'll use. T half is equal to 0.693 divided by K. Now that 0.693 is log 2, essentially, natural log of 2. But in order to make these calculations work out, we'll make it 0.693. So what that means is that K, therefore, will equal 0.693 divided by T half, which means it's 0.693 divided by 34.0 hours. Now that means that K will equal here 0.0204, and the unit there is hours to the -1, because that's going to be log 2, which doesn't have a unit, divided by hours, so it's hours to the -1 for the K. The next thing we need to do is apply this other equation that we have, negative KT log A over A0. Now the A over A0 is of interest to us because that's the fraction remaining. After time t. So the fraction that remains after time t. In this case, we are given a percentage here, 44.30%, which we can easily convert into a decimal, but we're just going to use the 44.30% as it is, and not subtract it from 100, because we're interested in what's going to happen if it remains, because that's the key word there in this particular question. So the time is what we're interested in. It's going to be log A over A0 divided by K. So that's going to be log of 0.4430 divided by the K, which we already calculated, 0204, and that's hours to -1. So the time we're going to come up with here is going to be 39.9 hours. Now this makes sense because if we look at the half-life, we can see that it's going to be 34.0 hours, and since this is more than 50%, because this is 34.0 hours is how much it would take to get to 50%, to get to 44.3% it's going to need a little bit more time than that, and 39.9 hours seems reasonable as an answer to that one. So what I'm going to do is I'm going to actually delete this so that I can have the room for the second question. And we're going to be starting again with the same situation. We've got T half is equal to 0.693 over K. K equals 0.693 over T half. That's the half-life. 0.693 divided by the half-life, which in this case is 665.1 hours. The K value we get for that is 0.00104, and again the unit is hours to the -1 on the K. The next thing we'll do is what we did earlier, negative KT is equal to log of A over A0, and again that's the fraction remaining. So what we're told here is that, well, what we're looking for is the time to decay, and what that means is I'm going to have to take this percentage and subtract it from 100 before I convert it into a fraction, because this is the fraction remaining over here, but what we're looking for is the time it takes to decay. So that would be what's remaining after 100%, or subtracting that remaining from 100%. So the time then is going to be log of 0.6990 divided by 0.00104 hours to the minus 1. So the way I get this 69.9 or 0.6990 is 100% minus 30.1%, and then divide that by 100, and that will allow me to get that decimal there for the amount that's actually remaining. So 30.1% has decayed. That means there's 69.9% remaining. And once we do that calculation, it comes out to be 344 hours. So that makes sense that it would take less time than the half-life. That would get it to 50%. We're actually going to try and get it only to about 70%, so it's going to take less time than the half-life, so 344 hours seems pretty reasonable.